Hello, everybody. I'm going to post a video version of the first tutorial. This is a compromise. The best way to do the tutorials is in a small group where you're actually interacting with your neighbor. But given that a lot of our students are having a hard time getting their schedule to work out with the tutorial, I thought I'd make this resource available. So let's go ahead and get started. I'm going to share my screen, and you should be seeing the tutorial handout now, if this is working. And what we have is a strobe diagram. And in this strobe diagram, we take pictures of a ball that's rolling up a ramp and slowing down. And the velocity vector is what we're asked to supply at each of these locations, 1, 2, 3, 4, 5, and 6. And the velocity vector is just a really, really simple concept. It's really almost visual. If you're going down the road in your car and you have any kind of imagination at all, it's just a big red vector that points out your front windshield. And the faster you're going, the longer it is. And so the velocity vector at 1 is going to be, that's not, is going to be up. Let's do it this way. It's going to be up the ramp and long. Once it gets to 2, it's slowed down a little bit, so the vector is not as long. And at 3, it's even shorter. 4, even shorter. 5, it's so small you can barely see it. And at 6, it's 0, because that's the turnaround point. And you've got to stop to turn around. Now, we call this a velocity diagram, and it shows both the location and the velocity of the object at instants in time that are separated by equal time intervals. Now, in the space provided here, we're asked to draw 3 vectors. We're asked to draw vector 1, vector 2, v1, v2, and the change in velocity. Now, if I want to move this vector down to this box, I have to preserve the 2 things that are very special about vectors, namely its magnitude, its length, and its direction. And so I'm going to have to draw that vector in a direction that's up the ramp and about the same length as what I have up there. And if I want to draw V2, again, I have to preserve the direction and the length. So it's going to be up the ramp and shorter. Now, I put those 2 vectors tail to tail. And that's because we're looking for a change vector. And that change vector is going to be the final, which is V2, minus the initial, which is V1. Now, remember, that vector can be thought of as what I have to add to the earlier vector to get the later vector. I can rewrite this equation by bringing negative v1 over to the other side of the equal sign, I can write it as v1 plus the change in velocity is equal to v2. In other words, the change vector is what I have to add to this long vector that I started with to get this short vector that I ended up with. And in order to make a long vector short, I have to add something in the opposite direction. Wish I had a better red pen. And so this would be my change in velocity vector. And you see, there's the plus sign right there. This long vector up the ramp plus this vector down the ramp is going to give me a shorter vector up the ramp. Now, we're asked, how does the direction of this change in velocity vector, delta v, compare to the direction of the velocity vectors? Well, the velocity vectors are up the ramp and the change vector is down the ramp, so they're opposite each other. Now, what if I had gone from 3 to 4? Would that change my answer? Think about that for a moment. Well, no, it wouldn't, because the vectors are still getting shorter as time goes on. My change vector is always going to be in the opposite direction of the velocity vectors. So the answer is no. And the explanation is just v final is always shorter than v initial for slowing. Okay. Now, if I turn this, well, that's special. If I go to the second page here, I'm given some information. I'm told that the initial value of v1 is posted here, and it's fairly large. And at a later time, when the second picture was taken, v2 has a smaller value, and so forth. The values just get smaller and smaller and smaller, and that's what this graph means. But the fact that it's a linear graph, that it's a straight line, tells us something about the change in velocity between any two time intervals, between any two time instances, I should say. During the first time interval, from v1 to v2, I have a change in velocity that's that big. If I look from, say, the time I took picture 3 to the time I took picture 4, the change in velocity is, well, the same size. It doesn't matter whether I look at picture 1 and picture 2 or picture 3 and picture 4, the value of the change in velocity is going to be the same in each of those cases. Now, what if we had gone all the way from 1 to 4? What if we had gone from this velocity here to this velocity there? Well, now the direction of the change in velocity vector is still going to be down the ramp. It's going to be the same. And that's because v4 is smaller than v1. So I'm going to have to add a change in the opposite direction. is the length of the change in velocity vector different than it was for consecutive points? Well, yes. For consecutive points, we said it was this big. And if I go all the way from V1 to V4, well, that's the time it took to take, that was 3 time intervals. From V1 to V2 is 1 time interval. From V2 to V3 is the 2nd time interval. And V3 to V4 is the 3rd time interval. So the change in velocity vector from 1 to 4 is going to be 3 times the change in velocity vector from 1 to 2. Because from 1 to 2, I only have 1 time interval. From 1 to 4, I have 3 time intervals. Now, the next part asks us to draw the direction of the acceleration vector using the definition of acceleration. Now, the definition of acceleration is just the change in velocity vector divided by the time interval. Now, if the change in velocity vector is down the ramp, the acceleration vector must also be down the ramp. I'd like you to take a moment. Oh, these two should be in the same direction. I just can't draw. You know what I mean. Now, the reason for this is clear if you recognize that time is always marching forward. We can't go backwards in time unless we have a DeLorean and a flux capacitor, if you saw the movie Back to the Future. So that means that I'm dividing this delta V vector by a positive number. Well, if I have any vector, let's call it the vector C. If I divide that by a positive number, let's say I divide it by 2, well, that's not going to change the direction of that vector C. It's just going to make it half as long. Okay. It's only if we multiply or divide by a negative number that we can change the direction with division or multiplication. And so that means that the acceleration vector must always, always, always be in the same direction as the change in velocity vector. These will be in the same direction. And the reason is delta t is positive. Does the acceleration change as the ball rolls up the track? Well, no. We find that for every equal time interval up here on this graph, let's say that time interval is, I don't know, 1/10 of a second. Well, for every 1/10 of a second, I've got exactly the same change in velocity. And so that means whether I go from 1 to 2, or from 3 to 4, or from 5 to 6, I'm always going to be dividing the same delta V by the same delta T. So the acceleration stays the same. The next part of this question said, well, what if you had 2 points that weren't successive? What if you went from 1 to 4? Well, if I went from 1 to 4, I would have 3 times the change in velocity that I would experience from 1 to 2, but I also would have 3 times the time interval. And the 3 cancels out in that equation. And so I get the same value for this acceleration from my definition, whether I'm looking at 2 points that are consecutive in time or whether I'm looking at points 1 and 4. Now, at the top of page 3, we're asked 2 questions. It says, generalize your results thus far to answer the following questions. What is the relationship between the direction of the acceleration and the direction of the velocity for an object moving in a straight line and slowing down? Now, this is a general question. Anything moving in a straight line and slowing down could be a car going down a straight freeway, hitting the brakes. Anything that's slowing down in a straight line, we have to have the acceleration and the velocity in opposite directions. Now, this next question is a very specific one. What about the case of a ball rolling up the ramp and slowing down? Well, since the ball is moving up the ramp, the velocity is up the ramp, and so that means the acceleration has to be opposite the velocity or down the ramp. So I would say the acceleration is down the ramp. Okay. So far, so good. Now we're going to do exactly the same thing, but with the ball going down the ramp. And it starts from rest. V6 is going to be 0. And then it's going slow at 7. And it's going faster at 8. It's going even faster at 9. Even faster at 10. And the fastest at 11. Okay. Now, if I take 2 points, I don't know, let's take 8 and 9 here. So my initial would be V8, and it's down the ramp, and my final would be V9, and it's also down the ramp, but longer. And again, I put them tail to tail because I'm looking for the change vector. Well, now the change is what I have to add to a short vector down the ramp to turn it into a long vector down the ramp. Well, to make a vector longer, I need to add something in the same direction. Okay. And there's a plus sign right there. This short vector down the ramp plus this change down the ramp gives me the long vector down the ramp. And again, that's what a change is. It's what I have to add to the initial to turn it into the final. Now, how does the direction of the change in velocity vector compare to the direction of the velocity vectors in this case? Well, they're both down the ramp, so they're in the same direction. And if I had taken 2 different points during the time interval, say 7 and 10, I'd still get the same answer, that the change vector is down the ramp, just like the velocity vectors. So it doesn't depend on which 2 vectors I choose, one of which has to be earlier in the day. In the space at the right, draw a vector to represent the acceleration of the ball between the points chosen above. Well, if the change in velocity vector is down the ramp, the acceleration vector must also be down the ramp. The acceleration vector and the change in velocity vector are always in the same direction. So the acceleration is down the ramp when the ball's going up and down the ramp when the ball's going down. And if I believe this graph right here, it's the same size at all of those instances. So now we've come to the last page. We are getting there. Again, we want to generalize our results thus far to answer the following questions. What is the relationship between the direction of the acceleration vector and the direction of the velocity vectors for an object that's moving in a straight line and speeding up? And again, it could be any object on a moving in a straight line and speeding up. Could be a car that's speeding up on a straight highway. Well, we just found that the acceleration vector and the velocity vector must be in the same direction. Now, the next question is a very specific question. Well, what about a ball that's rolling down a ramp? Well, the velocity vector is down the ramp. That's the direction the ball's going. And if it's speeding up, the acceleration has to be in the same direction as the velocity. So the acceleration is down the ramp. Now, let's look at the turnaround point where the velocity is equal to 0. In order to find an acceleration, we need 2 instances in time because we need a change in velocity vector to put into our definition of acceleration. If you want to know what the weather is like, stick your head out the window. But if you want to know how the weather is changing, you got to stick your head out the window, you got to pull it back in, you got to wait for 5 minutes, you got to stick your head out a second time to see whether it's different, whether there's a change. So in this case, I'm going to call this my V initial, and I'm going to call this my V final. Now you remember that when we were comparing vectors, V initial and V final, we always put them tail to tail. Okay, we always put them tail to tail. And that's what we have to do here. The V initial is up the ramp, and the V final is down the ramp. And again, I put them tail to tail so that I can compare them. Well, the change vector is what I have to add to the initial vector to get the final vector. So what do I have to add to this vector up the ramp to get a vector down the ramp? Well, I have to add a change that's big enough to send this initial vector up the ramp down to 0 and then out the other way. And so that would be my change in velocity. And there's the plus sign right there. They're stacked head to tail. Okay, so this initial vector up the ramp plus this change down the ramp gives me a final velocity down the ramp. And because the acceleration vector is always in the same direction as the change in velocity vector, my acceleration vector would be down the ramp. Notice that acceleration at the turnaround point is 0. Is not 0. I did not say that. It is not 0. It is not 0. It is not 0. I can't say that enough. It is not 0. If it were 0, the ball would roll up there, stop, and stay there forever. The acceleration is how much the velocity is going to change in the next little instant of time. And that ball is only stopped at the turnaround point for 1 instant. one tiny split instant, and then it starts rolling down the ramp. So the acceleration is not zero at that turnaround point. It's actually the same at the turnaround point as it is at all the other points. Well, that's been the tutorial. I have some obligations at home that I have to get to. So I'm just going to end this video, and we will stop sharing. Oh, that's me. And I will stop recording.